Hello, this is a joint work with Afrouz, Jabal, Ameli, and Vera, Traub. So in the survival network design family of problems, the basic goal is to design a chip network that supports a given traffic despite the failure of a few nodes or edges. And in particular, if we focus on edge connectivity and undirected graphs, there is this famous problem called Steiner network that captures several applications. So in this problem, we are given an undirected edge-weighted graph with sourcing pairs. For each sourcing pair, we also are given an integral requirement ki. And our goal is to find the cheapest subgraph such that for each pair SI-TI, there exists ki edge disjoint paths between SI and TI. In particular, even if you remove ki -1 edges, the pair SI-TI is still connected in your solution. A famous result by Jane shows that there exists a two approximation for this problem. And a well-known big open problem is improving on this two approximation, even by a little bit. Indeed, there are several special cases of this problem, which are also very interesting, for which two is the best known approximation. And so even improving on those special cases is an interesting problem. And this also motivates the title of this work, Breaching the Two Approximation Barrier. For many relevant problems, we managed to breach this barrier. Examples are the tree augmentation problem and its weighted version very recently, and then connectivity augmentation, for example, to edge connected spanning subgraph. Even the Steiner tree problem is a special case of Steiner network. And in this table, I just showed the first approximation factor below 2. But however, there are also other famous problems for which 2 is still the best known, like the weighted version of two-edge connected spanning subgraph and Steiner forest, for example. Now, let's focus on one special case of Steiner network, which is very well studied. It's called the tree augmentation problem. In this problem, we are given a connected graph plus a connection of extra edges called links. Our goal is to find a subset of links of minimum cardinality, such that if we add such links to the graph, then the graph becomes two-edge connected, like in the example. An observation is that in the input, without loss of generality, we can contract each cycle into a single node. Therefore, the input graph becomes a tree, and this motivates the name tree augmentation problem. So we can assume that the input is a tree. This problem is very well studied. There were many results, also some recent ones, and we have many better than two approximation algorithms. In this work, we address the question, what happens if instead of a single tree in the input, we have a forest? And therefore, we have also the issues of connecting the trees between them, besides achieving this two-edge connectivity. Now, this is the forest augmentation problem. In this case, for example, you can see that we need to add some links that connect the trees between them, but you might also have links inside the same tree of the forest, and this is in general needed. What's known for this problem? For the special case where the forest is just a collection of disjoint edges, this is called also the matching augmentation problem or MAP. In prior work, there are better than two approximation algorithms. Unfortunately, these algorithms do not generalize naturally. In particular, consider the path augmentation problem, which is the special case where the forest is a collection of paths. Then the above techniques do not apply to this case, and even to the special case where the paths just have length 2. So we really need new techniques to address the general case. So can we get a better than two approximation for the forest augmentation problem, or even for the path augmentation problem? And we answer affirmatively to this question by presenting a better than 2 approximation, even if only slightly better than 2. But hopefully future work will improve this approximation factor. And so let me give the idea of how this works. Let n trees denote the number of trees in the forest. And observe that the optimum solution opt must cost at least n trees. So the cardinality solution is at least the number of trees. Then the above theorem is the direct consequence of the following 2 lemmas. The first lemma works better when the number of trees is sufficiently smaller than opt and gives the approximation factor in the slide. So this factor for the number of trees going from opt to 0 moves from 2 plus epsilon to 1 plus logarithm of 2 plus epsilon. But an important observation is whenever the number of trees is by some epsilon prime factor smaller than opt, this approximation factor is strictly better than 2. So we are done in that case. The second lemma addresses the complementary case when the number of trees is close to opt. In this case, the approximation factor is 7/4 plus 13/4 times 1 minus the number of trees divided by opt. So when the number of trees is close to opt, this is roughly a 7/4 approximation, which is better than 2. So combining the 2 results, one directly, immediately gets the theorem. Now I will give some ideas about the 2 lemmas. So let's start with the few trees lemma. The first step in our construction is to build a 2 approximation for the forest augmentation instance. However, we construct this, there are several algorithms to achieve that. We use a very specific algorithm, which is as follows. We take the input, we bidirect the edges and the links. And now, using an old theorem by Edmonds, we can build for an arbitrary root R, we can build 2 edge disjoint spanning arborescences rooted in R, like in the picture. And we can find them of minimum weight. So let D be the union of these 2 arborescences. Then our solution consists simply of each undirected link such that we took at least 1 corresponding directed link. Sometimes we can take both copies of the directed link. So in the 2 directions. So and this is our solution, and it's not too difficult to show that this is a 2 approximation. Now, what do we do with this solution S? So first of all, we select in S a subset C of undirected links, such that adding this link to the input forest, we get a single tree. For example, in the picture, you see 1 possible choice. In this case, we have 2 trees, so 1 link is sufficient to get a single tree. And now let's look at the remaining links and the green links in the picture. We call this set U. Now, it is convenient to keep the original directions of these links in the previous step of the construction for a reason that we will see soon. Now, notice that these links U define a feasible solution to the tree augmentation instance that we obtain by adding C to our forest. And the cost of this solution is at most twice the optimum cost minus the number of trees plus 1. So we will use this quantity later. Now, let's call uplinks the links such that one endpoint is an ancestor of the other endpoint in the tree that we obtained rooted at R. So, for example, the 2 links on the left, you can check they are uplinks, but the bottom right link is not an uplink. And why it's not an uplink? So, in particular, you can see that the least common ancestor of the endpoints of this link is different from one endpoint of the link. Now we can transform U into another feasible solution to this weighted top instance. We call this solution U prime of exactly the same cardinality, but which contains only uplinks. So here there is a technicality that I'm not discussing. So we need to introduce the so-called shadow links, but this is without loss of generality to do that. How do we do this? This is fairly simple. For each link which is not an uplink, we replace that link with a link that starts at the tail of the original link and goes to the least common ancestor, like in the picture. Okay, like this. And why? It's not hard to check that this is also a feasible solution, and clearly that's the same cardinality. Why do we want uplinks only? And the reason is that we want to use this beautiful result by Traub and Zenklusen, which says that if you give me a weighted top solution U prime consisting only of uplinks, then we can find a better solution. And the cost of this solution is 1 plus logarithm, natural logarithm of the weight of U prime divided by opt plus epsilon, and this multiplied by opt. Now, for us, the weight of U prime is 2 opt minus number of trees plus 1, and so you can see that the modulo slight technicality, we start to have the result in the lemma. So the term n trees divided by opt in the approximation just comes from the link C that we added at the beginning. Then there is a -1, but this is just a little technicality. Now, let's move to the other lemma, the one that works better when there are many trees in the forest. So it is very convenient in this case to define a so-called rho k approximate solution. So such a solution for FAP has cost at most rho opt for some constant rho, let's say, and like in a normal approximation algorithms. But there is also an additive term, which is k times opt minus number of trees. So you can think about k being some large constant, because in our case, opt minus number of trees is something fairly small intuitively. And now, given this notion of rho k approximate solution, it is fairly easy to reduce the FAP input instance to a path augmentation instance. In particular, given a rho k approximation for PAP, you can derive a rho k plus 2 rho minus 1 approximation for FAP. And the reduction is also not difficult. So essentially what you do is you replace certain edges with a path of length 2 consisting of one link and one edge, like in the picture. And if you do this in the right order, then you get a collection of paths, and it's not hard to show that you achieve given a rho k approximation for this instance, you can convert into an approximation, rho k prime approximation for the original FAP instance for an appropriate k prime. So notice that reducing FAP to PAP is not trivial, while with this notion of rho k approximate solution, then it becomes fairly simple. So this was a critical idea. Notice also that rho k approximation is precisely what we need to prove the lemma, no? Where rho is 7 by 4 and k is 13 by 4. The second ingredient that we use, and this is the non-trivial part of the proof, is that we provide a 7 by 4, 7 by 4 approximation for PAP, for the path augmentation problem. And so in particular, if you plug in the numbers, you get the 13 over 4 in the above lemma. So how do we prove this? I can only sketch some of the basic ideas. First of all, we compute a maximum matching on the consisting of links only on the leaves of the paths, but we forbid links with both endpoints in the same path. Now, the intuition here is that if the matching size is much smaller than the number of paths, then the optimum solution has to be much bigger than the number of paths. And vice versa, if the matching is large, then we get very few paths, and this also helps us. So somehow it's a type of win-win approach. And then what do? We start with the infeasible solution given by this matching. Let's call this solution S, and we gradually transform S by adding and sometimes also removing links until S becomes a feasible solution. To keep the size of S under control, we use a credit assignment scheme, which is similar to prior work on related problems. So the idea is that we assign certain credits to the current solution, which is the graph G consisting of a collection of paths plus S, and the credits are non-negative. And then these credits are distributed on nodes, bridges, components, to edge connected components of the current solution. We keep the invariant that the size of the solution plus the number of credits is upper bounded by a quantity that we need to get a 7×4, 7×4 approximation, as you can imagine. However, there is a new idea in our approach, which is, in my opinion, which could be, in my opinion, very helpful in future work. This is the idea to assign some implicit credits. These are credits that are assigned based on some properties of an unknown optimum solution. So in previous work, to the best of my knowledge, credits were always assigned in an explicit way. So if you see the current solution, you know where the credits are. Now we don't know part of the credits where we don't know where they are assigned. Nonetheless, we can exploit them in the analysis. So this was very helpful and simplified a lot our proofs. Let me give a few more details about the steps of the construction. In our construction, to transform S into a feasible solution, there are two main phases. In a bridge covering phase, we guarantee that there are no more bridges in the current solution. So bridges are edges that if you remove them, you create one more component. And we remove bridges exploiting so-called what we call alternating trials. So in these alternating trials, we add some links to the solution such that adding them, some bridges disappear. And along the way, I mean, we also might merge together different connected components, like in the sample. And an important thing is that we also remove some links. To show that there exists a cheap enough alternating trials, so that the size invariant is maintained, we also sometimes use the implicit credits that I mentioned before. And in the second and final phase, which we call the gluing phase, we merge together. So we start with a graph whose connected components are also two-edge connected. And then we merge these components together. In particular, we can show that in some cases, there are so-called good cycles, which are cycles where we merge at least two edge connected components together, and we remove at least one link. And this is convenient for us. If such good cycles do not exist, then we can use the implicit credit somewhere to still merge two edge connected components together. So this is all. I conclude with two open problems that I shortly mentioned before. So in the weighted to edge connected spanning subgraph problem, we are given an edge weighted undered graph. And our goal is to find the cheapest subgraph, which is two edge connected. So for the unweighted version of the problem, we have better than two approximation algorithm, but for the weighted version, this is still open. And this is a generalization of the forest augmentation problem that I discussed in this talk. The second, even more famous problem is Steiner forest, where we are given an edge weighted undirected graph and a collection of pairs of nodes, SITI. And so we have to find the cheapest subgraph such that each pair is connected in this subgraph. So in particular, this is the special case of Steiner network, where the requirements are 0 or 1. And for both problems, a big open problem is to improve on a known to approximation. Thanks a lot.